Fluid dynamics and its biological and medical applications. So we talked about fluid statics. So fluids are anything liquid or gas. Fluid statics, we're just talking about density and pressure and buoyant force and all of those things that we get when a fluid is just sitting there. Fluids can move as well. So when we talk about fluid dynamics, talking about something like a fire hose, water moving through a hose. Typically the hose, you'll maybe have something at the end restricting the flow, so there'll be some unique properties there. So here we go, we're looking at a cross-section of a hose. We're looking at a specific volume of fluid moving through the hose. And there's all sorts of terms that we have here. We have the area, the cross-sectional area. We have the distance, the length of this little segment of fluid that we're talking about. It has velocity, and I'm sorry about this. I know physics can be a little obnoxious. So we have velocity, lowercase v, and volume, capital V. So make sure you don't get tripped up with those. We have Q. We have a few different Q's in physics too. Right now our Q is going to stand for this volume flow rate. So the flow rate is Q, which has a couple of different ways that we can bust it down to talk about it. So what do we have here? We have velocity, distance, time, volume. Distance over time then is velocity. So we have these terms that we'll be using. So right now the two ideas with fluid flow. There's steady flow, when the velocity of the fluid particles at any point is constant as time passes. In scientific circles you'll hear this referred to as laminar flow, so that's what we're talking about there. And then there's unsteady flow. That's when the velocity of the fluid particles at a point changes as time passes. And the extreme state of unsteady flow is turbulent flow. When the velocity of the fluid particles changes erratically in both magnitude and direction. What happens with turbulent flow is that we'll have changes in pressure. If you have changes in pressure, then particles can move up and down and over. So when your airplane encounters some turbulence, it'll encounter these areas of low pressure, and your airplane won't move through the fluid air very well. Fluids and fluid flow can be compressible or incompressible. Now, most liquids are nearly incompressible, but there are some that maybe have some compressible properties. And then gases can be compressed. So you know that you can squeeze something like, I don't know, nitrogen, and eventually it'll turn into liquid nitrogen. So it's less dense when it's a liquid, therefore it can be compressed to do that. Fluids can be viscous or non-viscous. A viscous fluid takes energy just to make it flow. So something like molasses. You tip the jar and it moves so slowly, and then eventually it starts pouring out. But that's energy that's going in just to making it move. Whereas I frequently look to coffee as my ideal of a non-viscous fluid, because it seems that I just set my mug down and I'm spilling coffee all over the place. It doesn't really take much energy to get it to move around. Now, you've probably heard of an ideal gas. Right now we're talking about the idea of an ideal fluid. Ideally, fluid's going to be incompressible, so we can bank on it having a certain density the whole time, and non-viscous, so we're not going to take energy just to get it to move. When fluid flow is steady, we use streamlines to represent the trajectory of the fluid particles. So we can study fluid flow in terms of making something more aerodynamic. And so then we have this concept of the mass flow rate. This is an important idea. The mass flow rate per second that flows through a tube is called the mass flow rate. So we have our hose and we're filling up a bucket, and I can say, hey, it takes me 30 seconds to fill up this bucket that has a volume of, I don't know, 12 liters. That'd be a big bucket. 2 liters, 4 liters. And so I could figure out the mass flow rate of the water through there. So the change in mass, so here we have this little cross-sectional area. It has the same volume of water as here, going through this bottleneck, which could be our garden hose with your thumb over the end of the hose, just representing it. So the change in mass is going to be density times volume, which is density times area times distance, and the distance is going to be velocity times time. See how that kind of broke out there? So the mass flow rate here in section 2, density 2 A2 V2, equals the mass flow rate here, because water's not being created or destroyed inside our pipe. It's all moving through it. It all has to go through every space the whole time. So we call this the equation of continuity. The mass flow rate has the same value at every position along a tube that has a single entry and a single exit for fluid flow. So rho 1 A1 V1 equals rho 2 A2 V2. Now, hopefully our liquid, since it's a liquid, is incompressible, so the density is not going to change. So for an incompressible fluid, we say A1 V1 equals A2 V2. And then back to that volume flow rate, Q equals area times the velocity. So for example, we're there with our garden hose. It has an unobstructed opening. It's got a cross-sectional area of 2.85 times 10 to the negative 4th meters squared. Going to fill a bucket with 8 times 10 to the negative 3rd cubic meter volume in 30 seconds. So there's our volume, or our mass flow rate. Then we want to find the speed of the water as it leaves the hose through the unobstructed opening, and then an obstructed opening with half as much area. So again, here's our flow rate. So V equals Q divided by A. So we can figure out V equals Q divided by A. So Q is the volume divided by the time divided by the area. We find out that with the unobstructed opening, the water's moving through there at 0.936 meters per second. And then, since we know that value, we can say A1 V1 equals A2 V2. When I put my thumb over the opening and cut it to about half, then the velocity will have to double in order to get all the water out in the same amount of time. So 2 times 0.936, 1.87 meters per second. All right, so this is kind of counterintuitive, but back here in the bottleneck is where we have high pressure. Down here, as we're getting to the opening, as we're getting out of there, is where we have a region of low pressure. And fluid accelerates toward the lower pressure region. Likewise, we have a case where if we have a pipe go through a change in height, according to the pressure-depth relationship, the pressure is lower at higher levels. Remember that we did this? P1 equals P2 plus rho GH. So the pressure is lower at the higher level and higher at the lower level. We can put these concepts together and think about the work it takes to lift up this water and bring it up here. Here we have two things going on. The pipe is narrowing and it's going up a hill. So if we consider the work, it's going to be the change in kinetic energy. So the total energy, kinetic energy plus gravitational potential energy for each of these different places on our pipe. And we could do some calculations there. All of this builds together into this one crazy equation. Now, we've talked about things like density equals mass over volume and how we can then have 3 different questions. But here we have pressure as a variable, density presumably is a variable, maybe it'll stay constant, velocity is a variable, g will be constant, but height will be a variable. So 1, 2, 3, 4 possible variables, 2 different positions in a pipe. This is a crazy difficult equation, except that we'll almost always simplify it somehow. So we'll go through a quick example or 2 here. Applying Bernoulli's equation, which is talking about the pressure the velocity and then the height difference of some sort of flow through a fluid. When the truck is stationary, the tarp lies flat, but when it's speeding down the highway, it lifts up. What's going on there? Well, we have a case where when the velocity of the fluid is faster, here as the truck is moving, when the velocity up here of the fluid is fast, the velocity down here is slow or zero, then we get regions of relative high and low pressure. If we have a region of relative low pressure up here, then we'll have a force that pushes it up. So conceptually, there's this sense. We see this conceptual idea with the design of airplane wings. If you have the airplane wing cutting through the air, then the air is a fluid that is moving around the airplane wing. Up at the top, we have a longer pathway for the air to move, therefore it must move faster. Down at the bottom, we have a shorter pathway. So if it's moving faster up top, it's a region of lower pressure. Therefore, we get this dynamic lift, and the wing tends to lift up. All sorts of applications in plumbing and baseball. In baseball, we have the curveball that's being thrown. As it's spinning around, on one side, it's kind of scooping the air and moving it past it. The other way, it's kind of cutting into the air. So with the slower air, there's higher pressure. With the faster air, there's lower pressure. And there's this deflection force that tends to make the ball move, spinning it that way. Here's another application. You can simplify it, but the idea with Bernoulli's equation here, we're going to look at pressure. Okay, pressure here and here are the same. We're going to look at velocity. The velocity of the liquid at the top of the drum sinking down as it's coming out the little spigot down here. The velocity coming down at the top of the drum is relatively slow compared to the velocity coming up here. Maybe we can pretend it's zero. That would make our math easier. And then what? Height. There's a height difference. There's the height at the top and the height at the bottom. Alright, so Bernoulli's equation, big bad equation, but P1, P2 equals atmospheric pressure. Those guys cancel out. 1/2 rho V1 squared, 1/2 rho V2 squared. Well, we're going to say V2 is essentially 0, so this whole term will disappear. And then rho G Y1, rho G Y2, Y2 minus Y1 is the height that we're talking about. So we simplify to 1/2 rho V1 squared equals rho G H, and then densities cancel out because the density is not changing. So then we solve for velocity and we get V equals the square root of 2gh. If you don't remember physics 1 stuff, I'll tell you that this is the same velocity that an object would have if I dropped it from this height and it just fell according to the acceleration due to gravity. So we have this little interesting conclusion where the water coming out the spigot at the bottom is going at the same velocity that it would go if it had fallen from this height. And indeed, if we turn the spigot upwards, it'll reach the same original height. Alright, viscous flow. This chapter now gets a little bit weird and talks about viscosity and different things that we're not going to get into. We need the skill set to be able to do thermodynamics and heat engines, and that's what we have now. We're not going to keep going into viscosity. So tackle this homework. You will be able to do it with what we've talked about, and you can look at the rest of the chapter for personal edification, but we're not going to be evaluated on those concepts at this time.